how to use common rate law equations and draw potential energy diagrams for some chemical reactions. It's really useful to know and predict how long something's going to hang around before it all decomposes, right? And that's pretty much what we're going to do. We're going to talk about these decomposition reactions where we have these reactants and they just go to products. So it's just one thing falling apart, okay? And we're going to do some math to review some math so we can apply those equations and use them. And then we're also going to talk about potential energy diagrams. And here's a real complicated one. It's done with supercomputers, but the reason why they do it is so that they can avoid, the reason why they create potential energy diagrams is so they can avoid doing all these experiments and sometimes dangerous or expensive experiments in the laboratory. They can use computers to predict how these chemical systems are going to behave and what they're going to do under different conditions. So that's why they use potential energy diagrams. So let's take a look at these common rate equations that we said we were going to use. So there's 3 sets of them. The homework will tell you whether it's a first order, a second order, or a 0th order reaction. So depending on what the homework tells you, you will use that set of equations. If they tell you it's first order, well then you've got 2 equations to work with. We just need to know what all these symbols mean. So let's take a look. You might recognize some, like K. That was our rate constant. Same rate constant we talked about before when writing rate laws. We've got T. T is for time. I think their convention is seconds, so they'll be sticking with that because the rate constants are almost always in seconds, so T is in seconds. Well, it's 20 seconds, 12 seconds, or whatever it is. We have brackets with a subscript 0. Whenever you see brackets, that means concentration. So that's the concentration of this reactant A at time T equals 0. Right? There's a 0 down there. And then we have a brackets with a subscript T. So that will be the concentration of A at time T. So if T is 20 seconds, bracket A with a subscript T will be the concentration of A at 20 seconds. So depending on whether it's first order, second order, or 0th order, you have a different equation to solve for, whether it's the concentration of A at time T or the original, that sort of thing. There's only one left, and that's half-life. That's T1/2. It's called half-life. And we'll talk about that pretty soon here, but that pretty much just means the time for exactly 1/2 of the reactant to disappear. The time for 1/2 of the reactant to decompose, that's the half-life. So let's do a little math review before we jump into solving these problems, because all of our homework is going to end up looking like one of these expressions, and we just solve for the variable. So let's take a look at this first one, A, and see if you can get a game plan. And do it all in one step in the calculator. Don't be writing anything down if you don't have to, because it's much less frustrating, I guarantee it. It's much less frustrating, and you get the right answer more often with the less you write down. So just let's try it. So my game plan in this is first to find what's inside this natural log. That's what ln is, natural log, and that button's on your calculator. I'm going to find out what that natural log is, hit equals, then I'm going to divide it by -89. That'll be my last step, and I'll get my answer. Okay? So, let's try it. 6.3 times 10 to the -3 divided by 3.9 times 10 to the -2, and I push the natural log button. I get about -1.82. Divide it by 89, and that's negative. You get about 0.02. Okay, let's try B. And we're going to do a little more writing on this one, I think. Otherwise, I might mess up. So we have to solve for this variable. We have to get rid of this natural log, because that variable's inside that natural log, right? There's really, you can draw in parentheses if you want. But how do you get rid of natural log? You raise both sides to the e power. Remember that? So if we raise this to the e power, we have to raise this to the e power. Okay? And then those cancel out. So what we really have here, I'm going to rewrite it, 2.49 times 10 to the negative 5 all over my variable, the initial concentration of A. That has to equal, well, let's see what that number is. E to the negative 0.35 times 5. So let's find out what it is. Let's take 0.35, make it negative, times 5, hit equals, raise it to the e power. I get about 0.174. Okay, now do you remember the little diagonal story? Right? I want to solve for A0, so let's just move it to the top. Move the 0.174 to the bottom, I'll be done. So my answer is going to be 2.49 times 10 to the negative 5 divided by 0.174. You get about 1.43 times 10 to the negative 4. Okay, here's another one. Okay, I want to solve for this variable. Do you see a game plan? My game plan that I see is this. And after you've done a bunch of these, it does get easier. I'm just going to figure out what this number is. Find out what that number is. Right? And then I'll just flip it and get my answer. Okay? So I'm going to start with that 2.4 times 10 to the negative 4. Okay, and it's in the bottom, so I'm going to push the 1 over x button, shift 1 over x, plus 12 times 18. So no parentheses, nothing. I just plugged it all straight into the calculator. And I got 4382.7. So I started with the 2.4 times 10 to the negative 4, did the 1 over x button on the calculator, so that flipped it, and then plus 12 times 18, I get 4382.7. Now I just need to flip that. Shift 1 over x. 2.28 times 10 to the negative 4. Okay. Here's another one where in D, see where that concentration of A at time t is, our variable? Our variable is inside the natural log, so we're going to have to raise both sides to the e power again. Raise everything to that. All right. Raise e to this power. So on this side, I'm going to get e to the negative 0.15 times 8. So let's find that. 0.15, make it negative, push that plus minus button, times 8, hit equals, shift e to the x, about 0.301. Okay, these cancel, so I'm just left with everything that was inside those parentheses. Okay, now I'm going to move things along the diagonal. I need to get this to the other side, so bring it up. Concentration of A at time t is going to be 0.301 times 7.2 times 10 to the negative 3. About 2.17 times 10 to the negative 3. Okay. Half-life. Here's a little demonstration of something radioactive. I don't know if you remember this device. It's a Geiger counter. And this is a piece of radioactive Tupperware. It's called Fiestaware. So half-life would be the time that we would have to wait around, right, for this count rate to go down by half? How long do you have to wait for that count rate to go down by half? In other words, for that radioactive material to decrease by 1/2 of its concentration. If the original concentration is 4.9 molar and each half-life is 5 seconds, what is the concentration of A after these amounts of time? Notice they didn't tell us which order. 0, first, second. They didn't tell us. So this is a concept question. So here's the trick to doing it. We're going to take that original concentration, whatever it was, take it times 1/2 to some power. And this power is always the number of half-lives that went by. Okay, let's try it. So this one, this first part, our original concentration is 4.9 molar. We have to take it times 1/2, raised to what power? How many half-lives went by? Just 1. Right? Because it's just 5 seconds. So 4.9 times 1/2 is about 2.45. Okay. The next one, we have to take our original concentration, right? I'm talking about this guy. The original concentration times 1/2 raised to the number of half-lives that went by. 20 seconds went by, so that means, right, what times 5 gives you 20? 4. It's 1/2 to the 4th. So 0.5 raised to the, so that's the x to the y button, 4, I get about 0.0625 times 4.9, 0.306 molar. Okay, the last one. We have 30 seconds. Well, 30 seconds, each half-life was 5 seconds. So what times 5 gives me 30? 6. So I have to take my original concentration times 1/2 6 times, or just raise it to the 6th power. So 0.5 raised to the 6th power is about 0.0156 times 4.9, about 0.076 molar. So that's the trick to doing these half-life problems when they don't tell you the order of the reaction. Okay, now let's change gears a little bit. Let's talk about these potential energy surfaces. Okay, here's an animation of one, and this is energy, and this axis is reaction progress, kind of. Okay, so right now, think of this as your chemical, and it's at a very low energy. Okay, it really can't go this direction. There's not enough energy. Let's start it up here then. Okay, and notice there's a problem here. He's got some energy. We can start him up here. He doesn't have quite enough to get over the energy hump. Okay, so you could give him more energy by heating him up, or you could lower this energy hump. Well, you really can't lower an energy hump. That's just characteristic of the reaction. So let's see if we can grab him here and give him a little more height. There he goes. Okay, so now he's down at a lower energy. So this would be an example of an exothermic reaction, because now the compound has a lower energy than it does up here. So this is an exothermic reaction, because where did the energy go? It just got released as heat. Let's see if we can draw a few of these. Know how to sketch these for exothermic and endothermic reactions. So we're starting out with an endothermic reaction. Okay, well, let's do the exothermic one first, since that's the one we just had a sketch on. Okay, let's do that one first. Exothermic. So we wanted to start high, and you want to end up low. Okay? So your curve kind of looks like this. You need a hump, an energy hump to come over, and you end up down there. Okay? They want us to label the axes. So this is energy, and the x-axis is called reaction coordinate. That's the x-axis here. They want us to label EA. That's the energy of activation. That's the energy hump that the reactants have to overcome. So that would be my energy of activation, right? The reactants had to overcome that energy hump. They want to know what delta H is for the reaction. That's going to be the energy difference between the reactants and the products. Well, here. So pretty much identify where the product is. And this energy difference right there, that is your enthalpy of your reaction. Okay, you can put a little Rx in there if you want, but the point is that's your enthalpy. And it's going to be negative. It's giving off a lot of heat. That's an exothermic reaction. Do the same now for an endothermic reaction. Okay, so we're going to have the same axes, energy, okay, we want to start out now. A and B have to start out at a low energy, and they end up at a high energy. Okay, so you draw the curve. Don't forget a hump. There you go. So what's my energy hump? My energy of activation, my EA. Well, it's more than this. Those reactants they started out down here. So that's my energy of activation. The enthalpy of the reaction, just the difference in energy between the products and reactants. Okay, so you know how to draw those diagrams for endothermic and exothermic reactions. A reaction of the form reactants going to products. Good, otherwise we can't use our equations. It's second order. Okay, here's the rate constant. There's our K. Right? If the initial concentration is 0.293, you'd probably start writing this stuff down. K is 0.225 liters per mole second. The initial concentration of A is 0.293 big M. And initial, remember, was bracket A times 0. What is the molar concentration of A? Right? What is the molar concentration of A at time 35.4 seconds? So T has to be 35.4 seconds. Okay, so I copied and pasted the equation here for you. So let's just substitute everything in. Notice how this is something you got to be careful of. The time is in the right units. Sometimes they're going to say that's in minutes and K is in seconds, and you have to do some converting. But here, everything's consistent, so let's just plug in all the numbers. It'll look better. 1 over the concentration of A at time T equals K 0.225 times T 35.4 plus 1 over the original concentration, which is 0.293. Okay, remember solving this one? We're going to get everything on that right-hand side and then just flip it, and we'll have our answer. 0.225 times 35.4 equals that, plus 0.293, flip it, 1 over x, hit equals. I get about 11.38. So flip that, and I'll have my answer. 0.088. 0.088. That's my final answer. Cyclobutane consists of some molecules in which 4 atoms form a ring. Decomposes when heated. Okay, good deal. The reaction is first order, so I'm giving you the first order equations. The initial concentration of cyclobutane was, we should probably write this down. Initial concentration was 0.0015. After heating for 455 seconds, T is 455 seconds, this was reduced to 0.00119. 0.00119 molar. So what variable is that? Right? What was the concentration of cyclobutane after a total of 750 seconds? So now we've got 2 of these. What's the concentration of cyclobutane at T equals 750 seconds? That's what we want to find. Okay. Do you see what's going on here? Why'd they give us all this information? It seems like this extra stuff. Well, what we're going to do is, if we wanted to solve for this right here, we would plug everything in, and notice we're missing K. We don't know what K is, so we can't find this. We have to find K first. That's why they gave us all this. So let's use this to find K. Then we'll solve that. Okay? Okay, so let's give this a shot. So let's find K first. We have the natural log, using that original data here. Natural log of A at time t has to be 0.00119 all over the original 0.0015 has to equal a negative K times 455 seconds. Okay, so let's solve for K. We'll have 0.00119 divided by 0.0015. It equals natural log. Divide it by 455, negative 455. I get about 5.088 times 10 to the negative 4 is my K. Okay, now I'm ready to solve for the last part. Okay, apply the equation again. I'll have the natural log. Now I want to find the concentration of A at time t. The original doesn't change. That's still 0.0015. Has to equal a negative K, which is 5.088 times 10 to the negative 4 times t. Now my t is 750 seconds. Okay? So see if you can get this. I'm going to do it all in one step on that calculator. Okay? This is how I'm going to do it. 5.088 times 10 to the negative 4. Let's make that negative. Times 750. Raise it to the e power. Take it times 0.0015. And I have my answer. 1.02 times 10 to the negative 3. And if you had to write some intermediate steps, that's fine, but try to minimize that. Okay? In the presence of excess thiocyanate, the following reaction is first order in chromium. And the rate constant is 2 times 10 to the negative 6. What is the half-life in hours? Okay, they say, what is the half-life in hours? Here's our equation. We needed to be 0.693 all over K. Okay. They told us the rate constant. All over 2 times 10 to the negative 6. Now that's going to be in seconds, so we're going to have to do some converting here. But 0.693 divided by 2 times 10 to the negative 6, you get about 346, 500. So that's my half-life. Now, realize that is in seconds, though. They want the answer in hours. So times 60 seconds in a minute. And there's 60 minutes in an hour. Right? My minutes cancel, my seconds cancel, and I'll be in hours. So take that, divide it by 60 twice. You get about 96.25 hours. Okay. Now, how many hours would be required for the initial concentration to decrease each of the following values? Okay, and there's a hint here. We could use this expression to find the answer, but I think it's easier if you use the definition of a half-life. So 25% left. How long? Well, 25% is 0.25, which is a fourth. And recognize a fourth is a half times a half. That's 2 half-lives. Well, each half-life was how long? 96.25 hours. So need 2 of those. Around 192.5 hours. Let's try it again. 1/8, which is 12.5%. Okay, that is equal to 1/8. But that is equal to a half times a half times a half, right? That's 3 half-lives. So take 3 half-lives. 3 times 96.25. 96.25 times 3, you get about 288, 289 hours. Uh, 16th, which was 6.25%. That's equal to a 16th. And that's equal to 1/2 to the, what, 4th? 4 half-lives. 4 half-lives. So take the half-life then times 4. 4 times 96.25. 96.25 times 4, about 385 hours. The last one is 3.125%. 3.125%. Okay, that's just another half. So now it's going to be 5 half-lives, right? 1/2 to the 5th. Right, take 1/2 times itself 5 times and you get 1/32. So 96.25 times 5. And I get about 481 hours. Okay. A reaction is of this form, okay? Second order with a rate constant of 0.169. Okay, so we need our second order expression. Here's second order. 1/a at time t equals kt plus 1/a0. Okay. So they told us some things here. They said the rate constant is 0.169. K is 0.169. It's in seconds. The initial is 0.159 molar. How many seconds, so T equals question mark, would it take for you to get all the way down to 6 times 10 to the negative 3 molar? So the concentration of A at time T is 6.07 times 10 to the negative 3 molar. Okay, so let's substitute in, solve for T. K is 0.169. T plus 1 over the original 0.159. Okay, solve for T. So again, I'm going to do it all in one step on the calculator. I'm going to take 1 divided by 6.07 times 10 to the negative 3, hit equals, subtract 1 divided by 0.159, hit equals, divide it by 0.169, and they get about 938 seconds. Okay, so the game plan here is pretty much, right, pick the right equation, substitute everything in, and solve for the unknown variable.